early 1916, Albert Einstein completed the greatest work of his career. It was the result of decades of arduous intellectual labor to construct a new theory of gravity, what he called the general theory of relativity. However, this is not just a new theory of gravity, but also a groundbreaking theory of space and time. And this is also the first scientific theory that not only explains how objects move in the universe but also clarifies how the universe itself can evolve. However, there was still a problem. When Einstein applied his theory to describe the entire universe, he realized it didn't match the universe we live in. Now, after hundreds of years, it is almost impossible to measure just how profoundly humanity's worldview has transformed within a single lifetime. In 1917, the scientific community believed that the universe was static and eternal, consisting solely of a single galaxy, the Milky Way, encased in an immense, dark, and infinite void. After all, that is what you could observe when gazing at the night sky with the naked eye or through a telescope, and at that time, there was no reason to suspect there was anything else out there. S theory of relativity as well as Newton. This means that a group of objects with mass cannot remain permanently at rest in space. The attraction between them will pull them crashing into each other, completely contrary to an inherently static universe. Einstein's theory of relativity seemed incompatible with the prevailing conception of the universe at the time, and this shocked him more than you might imagine. Many people still believe that Einstein spent years working alone in a closed-off room. Relying solely on thought and reason, grasping his brilliant theory will remain disconnected from practice. However, nothing can distort the truth. Einstein was always guided by experiments and observations from the depths of his mind. He spent decades tirelessly pondering and wrestling with countless thought experiments in his mind. He learned many new mathematical concepts but followed flawed theoretical guidance throughout the process. Finally, he discovered an incredibly subtle and beautiful mathematical theory. However, the most pivotal moment that shaped his love for general relativity was. This once again ties closely to the activity of observation. In the final 10 weeks, he had to rush to complete his theory to compete with the German mathematician David Hilbert. He used his equations to calculate and predict an astrophysical phenomenon that had remained unexplained up to that point. S orbit slightly differs from Newton. Instead of moving in a perfect elliptical orbit and returning to its starting point, Mercury has a slightly shifted orbit due to the phenomenon of precession. This means the planet does not return to its exact original position after each orbital cycle, but the orientation of Elis shifts slightly with each revolution. Finally, draw a spiral with an extremely small value, just 43 arcseconds per century. When Einstein calculated this orbit using general relativity, the results matched perfectly. However, the clear discrepancy between general relativity and actual observations indicates that a static universe cannot endure long-term. Today, everyone knows that the universe is not static but is constantly expanding. And this expansion originated from an extremely hot and dense Big Bang, which occurred approximately 13.8 billion years ago. Another extremely important point is that we need to understand our Milky Way is just one of roughly 400 billion known galaxies in the universe. We are like primitive explorers, tentatively sketching the map of the universe at its grandest scales, still in the earliest stages of discovery. It comes as no surprise that recent decades have witnessed revolutionary changes in our understanding of the universe. The discovery that the universe is not static but continuously expanding carries profound philosophical and religious significance. Because it suggests the idea that our universe had a beginning. A new beginning always holds creativity, and it is that very creativity that will ignite intense emotions. Although the discovery of the expanding universe was announced in 1929, it took several more decades for the Big Bang theory to receive independent experimental evidence confirming it. But as early as 1951, Pope Pius XII proclaimed this as authentic evidence for the Book of Genesis. As you once asserted, modern science seems to be looking backward through the centuries. Successfully verified the authenticity of the Djifoot Winnie created by Pius XI Nguyen Tui. From the dawn of time, when all things emerged from the void, they burst forth into an ocean of light and all-encompassing radiation. And the elements within were dispersed, exploded, and then formed millions of galaxies. Therefore, with reliable physical evidence, we have confirmed the unexpected birth of the universe. And that is also a compelling interpretation of the era when the world was shaped by the hand of the Creator. Thus, creativity came into being. As the saying goes, to create is to exist, and it is through this that God exists. The full story is actually even more fascinating. Few people know that the first person to propose the Big Bang Theory was actually the Belgian priest and physicist named Georges Lemaitre. He is a man of profound knowledge in many fields. His research career began when he was an honored artillery engineer. 1 month of boxing, then switched to mathematics while attending seminary in the early 1920s. Later, he shifted his focus to astronomy and began collaborating on research with a British astronomer. Before attending Harvard University and later earning his second doctorate, Sir Arthur Stanley Eddington took his first steps in his academic career. The physics department at Mead University. In 1927, before earning his second doctorate, Lemaitre conducted. Ra had solved the equations in Einstein's general theory of relativity and proved that this theory, predicting a universe that is not static, while affirming that the universe we live in is indeed expanding. This view seems to have gone too far, to the point where even Einstein himself had to strongly oppose it. When published, the mathematical part of his research was accurate, but the physics part was terrible. Nevertheless, Lemaitre persevered, and by 1930, he had made even greater strides. One hypothesis suggests that our expanding universe actually originated from an infinitely tiny point. He called it Bremen van Item, the primordial atom, and suggested that this starting point might have been what was alluded to in Genesis as a day without a past. Therefore, in essence, the Big Bang and Pope Pius XII proclaimed was originally the discovery of a priest. It is believed that Lemaitre would have been thrilled by the Pope's confirmation. But in reality, he completely dismissed the idea that this scientific research would have theological implications. Finally, he omitted a section from his 1931 article on the Big Bang, where he discussed this issue. In fact, Lemaitre later opposed the Pope's 1951 statement when he claimed that the Big Bang was evidence proving the book of Genesis. Not only because he understood that if his theory was later proven wrong, the Vatican's statements on the book of Genesis may face criticism. By that time, he had been elected to the Vatican Pontifical Academy and later became its president. From what I understand, he once stated that such a scientific system is always separate from any issues related to theology or religion. The Pope never publicly mentioned that topic again. Here lies an extremely valuable lesson, as Lemaitre once noted. Whether the Big Bang actually happened is a scientific issue, not a theological question. Moreover, even if the Big Bang truly occurred, humans could still choose to interpret this event from various perspectives. Depending on each person's religious inclination or metaphysical belief, you can view the Big Bang event as a starting point of creation, depending on your personal perspective. You might think that the algorithms in general relativity explain the evolution of the universe from its earliest moments without the need for any divine intervention. However, such a metaphysical speculation is entirely separate from the physical meaning of the Big Bang and has no bearing on our understanding of the event. Of course, once we move far beyond the notion of a merely expanding universe, to explore the principles of physics, helping us trace back to their origins, science can shed deeper light on this hypothesis, and as the above analyses have shown, it has indeed done so. Under no circumstances could either Lemaitre or Pope Pius convince the scientific community that the universe was expanding. More precisely, like all genuine sciences, evidence is drawn from meticulous and careful observations. In this case, Edwin Hooke was the one who made that observation. He instilled in me a strong belief in humanity, especially since he began his career as a lawyer before transitioning into becoming an astronomer. In 1925, Edwin Hubble made a crucial breakthrough thanks to the Hooker telescope. With a circumference of 100 inches, this is the largest telescope in the world when placed atop Mount Wilson. By that time, thanks to the available telescopes, astronomers were able to observe more clearly the faint images of objects that were not just individual stars in the Milky Way. They call them nebulae. They still debate whether these entities lie within our galaxy or beyond it. Since the prevailing view at the time held that our Milky Way constituted the entire observable universe, most astronomers were confined to studying the scope of their own galaxy. Leading the pack is the renowned astronomer Hello Subley from Harvard University. Subley dropped out of school in 5th grade, but later he taught himself and eventually got accepted into Princeton University. He chose to study astronomy simply because it was the first subject he saw on the list. In his groundbreaking work, he demonstrated that the Milky Way is far larger than previously thought, while also confirming that the Sun is not at its center but merely an ordinary star on its distant outskirts. He was a highly influential figure in the field of astronomy, so his views on the nature of nebulae carried significant weight. Spiral nebulae, where he could discover a special type of variable star, known as the Safed variable star. In this celestial object, including the one we now know as the Andromeda Nebula. First discovered in 1784, Seyfert variable stars are stars whose brightness changes in a specific cycle. In 1908, there was a little-known and unrecognized figure who was a talented astronomer at the time. Human computer. She was the daughter of a pastor from an autonomous congregation and a descendant of the Pilgrims. In 1912, Leavitt made an astonishing discovery and later explained it even more clearly. She noticed a consistent correlation between the brightness of Seyfert variable stars and their luminosity variation cycles. If it is possible to determine the distance to a Seyfert star with a known variability period, measuring the brightness of other Seyfert stars with the same variability period will help determine their distances. The observable brightness of stars is inversely proportional to the square of their distance from Earth. Determining the distances to distant stars has long been a major challenge in astronomy. Leavitt's discovery marked a revolutionary turning point in this field. The official paperwork has been initiated at the Royal Swedish Academy to consider Leavitt's nomination for the Nobel Prize in 1924. Everyone believed she had passed away from cancer 3 years ago, due to the influence of personal factors, self-promotion skills, and the observer's professional expertise. Edwin Hooper is so famous that everyone knows him, while Leavitt, unfortunately, is only mentioned among passionate professionals. You can apply your measurement to the Seifeld stars and the relationship between their cycle and brightness. Leavitt discovered this to clearly demonstrate that the stars in the Andromeda Galaxy and many other more distant galaxies are far too remote to belong to our Milky Way. The Andromeda Nebula was identified as a distinct galaxy in the universe. A spiral galaxy, similar to our own, is one of over 100 billion other galaxies that humans have discovered so far. They exist within the observable universe. The research findings from Hooper were presented clearly, enabling the astronomy community to quickly acknowledge the fact that the universe is not limited to just the Milky Way galaxy we live in. In just one leap, the scale of the universe suddenly expanded far beyond all the knowledge accumulated over centuries before. Its nature has also changed, like most other things. After this important discovery, Hooper was able to peacefully enjoy his glory. But he was aiming for a bigger target, or more specifically in this case, the giant galaxies. By measuring the faint Seyfert stars in more distant galaxies, he was able to expand the map of the universe on larger scales. Adapting on the fly, in the midst of action, he suddenly realized something far more important. The universe is expanding. Hooper achieved that result by analyzing the distances between galaxies he had measured. According to a series of measurements by another American astronomer, his name was Vesto Slipher, the one who conducted spectral measurements from these galaxies. To fully understand the existence and nature of these spectra, let's turn back time and return to the very dawn of modern astronomy. One of the most significant discoveries in astronomy is the material that forms stars. And the matter on Earth is largely similar to each other. All of this began, like many other discoveries in modern science, with Isaac Newton himself. In 1665, Newton, then a young scientist, used a small prism to split sunlight. The light was obtained by darkening the room, leaving only a small hole he had made at the top of the window. Stepping through a pane of glass, I saw the sunlight burst into a dazzling array of colors, like a rainbow. He proved that white light from the sun is a combination of all colors, and this is entirely accurate. A century and a half later, another researcher conducted a more thorough analysis of that light dispersion phenomenon. Scientists have discovered dark lines interspersed among the spectral color bands and explained that this phenomenon occurs due to the presence of matter in the sun's outer atmospheric layer. These scales always absorb light with specific colors or wavelengths, and later they were called absorption scales. The wavelengths of light absorbed by known substances on Earth, including helium, oxygen, iron, sodium, and calcium, can be determined. In 1868, another scientist discovered two absorption lines in the yellow spectrum of sunlight. Without matching any known elements on Earth, He confidently asserted that this must be a new substance and named it helium. A century later, helium was first discovered and successfully extracted on Earth. Spectroscopic analysis of stellar radiation is a fundamental scientific method for studying their composition, temperature, and evolutionary processes. Since 1912, Schleifer has studied the light spectra emitted by various spiral nebulae and observed that they share characteristics similar to the spectra of nearby stars. Except for this, all absorption lines are shifted by the same amount in wavelength. This phenomenon was later explained similarly to the Doppler effect, named after Austrian physicist Christian Doppler. In 1842, Doppler proved that when waves are emitted from a moving source, the wavelength stretches as they reach an observer. If this source moves away from the table, it will stretch. Conversely, if it moves toward the table, it will compress. Here are the natural English translations for your Vietnamese text. Like the whistle of a train or the siren of an ambulance, the sound grows higher as they approach you. And it will slow down as it moves away from the table. And it turns out, this phenomenon doesn't only occur with sound waves but also similarly applies to light waves. Even if for slightly different reasons. The light is emitted from a source moving away from the table. Due to its motion through space or the expansion of the space between galaxies will be stretched out. And so, it looks redder than before. Because red has the longest wavelength in the visible light spectrum. As waves move toward the shore, they compress and become bluer. In 1912, Schleifer observed that the light emitted from spiral nebulae was all redshifted. Almost systematically shifted toward longer wavelengths. He reached the correct conclusion. Therefore, most of these objects are moving away from us at significant speeds. Hubble can compare its observations of the distances between these spiral galaxies. Measurements of the galaxies. In 1929, with the assistance of Milton Humason, a staff member at the Mount Wilson Observatory, Hubble asserts that he has discovered a remarkable connection through experimentation. Today, it is known as Hubble's law. The speed at which galaxies move apart is directly proportional to the distance between them. That means, the farther away a galaxy is from us, the faster it moves. When this remarkable truth was first revealed, that the vast majority of galaxies are continuously moving away from us. And celestial objects twice as far away move twice as fast, those 3 times as distant move 3 times as fast. When Hubble and Humason first announced their analysis results in 1929, they not only clarify the linear relationship between distance and remote movement speed, while also providing a quantitative assessment of the expansion speed. The expansion speed of these galaxies suggests there may be a planet located about 1 million light-years away. Equivalent to a distance of 3 million light-years, it is moving away from us at a speed of 500 kilometers per second. This is quite easy to verify. If everything is drifting apart as it is now, then they must have once been very close. If gravity were truly an attractive force, it would slow down the expansion of the universe in the future. This means the galaxies we observe today are moving away from us at a speed of 500 kilometers per second. Before, the train used to move at a faster speed. However, if at this very moment we simply conclude that the universe has always been expanding at such a rate, we need to go for it to align with our galaxy. Because galaxies twice as far away also move twice as fast. From the opposite perspective, we can see that they were planted in our exact positions at the same time. Indeed, the entire observable universe we see today originated from a single point. The Big Bang point, at the moment we can estimate in this way. However, this calculation clearly indicates an upper limit on the age of the universe. If people had ever moved faster, they may have reached their current position in a shorter time than initially estimated. Based on Hubble's analysis, calculations indicate that the Big Bang occurred approximately 1.5 billion years ago. However, as early as 1929, evidence clearly showed that our Earth is over 3 billion years old. At this moment, scientists are truly baffled to discover that Earth is located farther out in the universe than previous calculations had suggested. More importantly, this indicates that the above analysis has some flaws. The origin of this irony lies precisely in the distance that Hubble had estimated. The application of the South-Safe Fate correlation within our Milky Way is systematically inaccurate. And then, calculate the distance to galaxies even farther than the South-Safe Fate celestial objects previously observed. That kind of promotion is not right. This is a stunning spiral galaxy, located in the far distant reaches of space, from an ancient time long ago. A spiral galaxy like this is quite similar to our Milky Way, containing around 100 billion stars within it. The glowing core at the center of a galaxy can often contain up to 10 billion stars. Look at the brilliantly shining star in the lower left corner. Its light is nearly equal to the combined light of those other 10 billion stars. At first glance, you might think it's just a nearby star in the Milky Way that accidentally wandered into the frame. But in reality, it's a star from a distant galaxy, more than 50 million light years away from us. Clearly, this is no ordinary star, but one that has just exploded, a supernova, one of the most dazzling spectacles in the universe. When a star explodes, it erupts in a dazzling burst of light, shining 10 billion times brighter than a normal star. We are fortunate that stars rarely explode, with an average of only once every 100 years per galaxy. Fortunately, those bombs exploded, otherwise, we might not even be here now. One of the most poetically beautiful truths I've ever known about the universe is this: by nature, every atom in your body once belonged to a star that exploded in the vastness of space. Moreover, the atoms in your left hand may have originated from a different star than those in your right hand. Literally, we are all born from the stars, and this body of ours is essentially made of stardust. How do we know this? Because we can trace the cosmic picture backward from the Big Bang to the moment the universe was just 1 second old. We calculate that all observed matter could be compressed into a special form of plasma with temperatures reaching up to 10 billion Kelvin. At that temperature, nuclear reactions can easily occur between protons and neutrons as they collide and then separate after those collisions. After this process, the universe gradually cooled down. We can predict that the primordial nuclear elements would combine to form heavier atomic nuclei, such as helium, lithium, and so on. When analyzed this way, we find that essentially no nuclei exist beyond lithium, the third lightest atom in nature. Formed during the occurrence of the primordial fireball, what we now call the Big Bang. We are completely confident in the accuracy of current measurements, as predictions about the abundance of the lightest elements in the universe match these experimental observations with remarkable precision. The abundances of the lightest elements, hetron, dilfree, haley, and lithium, vary across a range of 10 orders of magnitude. At this astonishing level, empirical observations and theoretical predictions align perfectly with each other. This is one of the most accurate, profound, and widely recognized predictions. This proves that the Big Bang truly occurred. Only a hot Big Bang explosion could produce the abundance of light elements we observe, while sustaining the universe's relentless expansion, a phenomenon that continues to this day. While lithium is important for a small number of people, for most of us, heavier elements like carbon, nitrogen, oxygen, or iron hold far greater significance. These substances did not form in the Big Bang. The only place they can form is in the fiery cores of stars. Today, these elements can only enter your body if stars are generous enough to explode, scattering their products throughout the universe. One day, they may gather again, circling around a tiny blue planet near the star we call the Sun. In the history of the Milky Way, around 200 million stars have ended their life cycles in brilliant explosions. Millions of those stars dissolved into the cosmos, only for their atoms to one day become part of your very existence. It turns out that a special type of exploding star, called a Type 1a supernova, was proven through meticulous studies published in the 1990s to be of immense importance. Type 1a supernovae have extremely high precision. They are not only significantly brighter but also emit light for a longer duration. This correlation, though not yet fully explained theoretically, is clearly observed in practice. This indicates that these supernovae are indeed reliable standard candles. This means these supernovae can serve as a basis for measuring distance, since their intrinsic brightness can be directly determined through independent measurement, independent of distance. When observing a supernova from a distant galaxy, extremely bright objects visible from Earth, we only need to measure its duration of brightness to estimate its true luminosity. After that, by measuring brightness through the telescope, we can accurately determine the distance from the supernova to its host galaxy. Then, by measuring the redshift of light from stars to galaxies, we can determine their velocity. From there, comparing the velocity with the distance allows us to predict the expansion rate of the universe. Everything is normal, but if a supernova only explodes once every 100 years or in each galaxy, how many of us are lucky enough to witness such an explosion firsthand? Finally, the last supernova in the Milky Way observed from Earth was in 1604, by astronomer Johannes Kepler. In reality, it is believed that a supernova in our Milky Way galaxy appears only once during the careers of the greatest astronomers, and Kepler was one of them. He started his career as a humble math teacher in Austria. Kepler became the assistant to astronomer Tycho Brahe and used the data Brahe had painstakingly collected over more than 10 years on the positions of celestial bodies in the sky. Kepler announced 3 famous laws of planetary motion in the early 17th century, collectively known as Kepler's laws of celestial motion. First, the planets move around the Sun in elliptical orbits. The second is Kepler's second law, which states that a planet orbiting the Sun sweeps out equal areas in equal intervals of time. Third, the square of a planet's orbital period is directly proportional to the cube of the semi-major axis of its elliptical orbit. These laws later became the foundation for Newton's discoveries on the law of universal gravitation nearly a century later. Nowadays, observing supernovae has become simpler by assigning each student to monitor a galaxy in the sky. After all, 100 years isn't too long, at least compared to the lifespan of the universe. The time required to earn a PhD is often quite long, while the salary for graduate researchers is low, leaving many feeling discouraged. Fortunately, we didn't have to resort to such drastic measures in the end. Because of a simple reason: the universe is vast and ancient beyond measure. Thus, those rare events still occur everywhere. Step outside, into the deep forest or desert late at night, where you can gaze at the stars. Raise your hand to the sky, forming a small circle the size of a coin between your thumb and index finger. Amidst the vast expanse, who lifted his gaze to a patch of pitch-black sky, where not a single star twinkled? In that dark region, if you use a sufficiently large telescope like the modern ones today, you could observe around 100,000 galaxies. Each galaxy contains billions of stars. Therefore, on average, a supernova explodes in a galaxy every 100 years. Every time you look up at the night sky with its 100,000 galaxies, you're witnessing an average of 3 stellar explosions happening. The astronomers followed the correct procedure. They booked observation time to use the telescope. On some nights, they could see bright shooting stars. There were nights when 2 streaks appeared at the same time. But there were also nights when the sky was covered in clouds, revealing nothing but a thick, impenetrable darkness. Here's the translation, adapted to both contexts. The new figure, approximately 70 kilometers on the wire, corresponds to an average distance between galaxies of 3 million light-years. Only 1/10 of the figure proposed by Hubble and Hermison. The results show that the universe is nearly 13 billion years old, not 1.5 billion years as initially predicted. This is entirely consistent with independent estimates of the age of the oldest stars in the Milky Way. From Brahe to Kepler, from Lemaitre to Einstein and Hubble, and from the spectra of stars to the abundance of light elements. 400 years of modern scientific development have painted a unified picture of an expanding universe. Everything is intricately connected, and the picture of our universe is gradually becoming clearer.